gravity, so we need gravity equation for gravity potential. Then the next we need the equation of state, and also we need energy equation, which better to write down in entropy term. And the final equation, but perhaps the most important one is Navier-Stokes equation. We consider it in detail. In this machine is working in such a way that we have liquid core of the planet, or in some planets it's not core, it's maybe some metallic hydrogen like in Jupiter, and it could be another substance. But even there is icy planets like Neptune and Uranus, and here we have icy stuff which becomes under this huge pressure in the near the center of the planet very strong, so it's become metallized, and it has some conductivity as well. Everything is working on conductivity in terms of creating the magnetic field, which we can examine straight out. But in fact, there is also some contribution of the convection. If no convection exists, then there is no dynamo as well exist. Moreover, it could be a situation when the convection exists, but there is no dynamo, which perhaps occurs in the modern Mars, in the Venus, and so on, because definitely there is some convection there, but it's not so strong to support the magnetic field. So the subject for studying the convection itself was to be pushed out. And so I just show you all the equations. Then we use, first of all, we of course related to the Earth, and for the Earth we just estimated different values, and using this value we can estimate different term in these equations which I showed you previously. And it's important conclusion that first of all, as thermodynamic variable, we should explore the pressure and entropy, or more precisely not the pressure entropy itself, which is here noted by the capital letters, but the deviation from the adiabatic pressure and correspondingly from adiabatic entropy. And also there is also deviation from the adiabatic gravity potential. So all these three most important components, together of course with velocity, they constitute the convection system. And but we effectively remove temperature from the system. But nevertheless, we use that there is small deviation of the temperature from adiabatic state, which this adiabatic state marked everywhere by the subscript A. And so we then expand the deviation of the temperature in terms of the super adiabatic pressure and super adiabatic entropy. Anyhow, this okay, I will just say pressure and entropy, not saying that it's super adiabatic, that is some addition on top of adiabatic value, because finally we investigate them, so why not to repeat all the same. So P small and C small, and I will simply call pressure and entropy, while of course it's a deviation. And it also can be expressed directly in the measurable things. There is adiabatic temperature, very well known for the Earth, and from the seismic data there is Cp, also very well known, and also there is the expansion coefficient. Unfortunately, it's not so very well known, but order of magnitude with accuracy of about 10%, 10 or 20%, we can explore it. And again, there is also adiabatic density, and in the similar relation we can also relate the density, and it's also very well known again. And this is representation. So it's interesting to know that there is also very valuable term in all this equation, which I will show you later, and this is actually constitute that the adiabatic entropy is not dependent on any special coordinate. It depends only on time. So the gradient of adiabatic adiabatic entropy is dependent only on time. And what represents this dependence of time? We put it like S over dot. So it's more simple stuff, and it could be roughly estimated like the output heat flux which coming out from the planets, and then we divide it by mass of the liquid part of this deep interior of the planet, and of course also we multiply by some again TC here. This means that this reference on core. So in case of the Earth, this is this first will be the mass of the liquid core, and the TC here is an average temperature of the core. But of course, if we consider not the Earth and Earth-type planets, we will go not the liquid core, but also, for example, in Jupiter we have metallized hydrogen on some depths, and so it's sort of the metallized hydrogen which becomes the property of liquid, but still keeps some gaseous properties. But and it's quite important that this relation constitutes the process of the cooling down of the planets. More precisely, not all planets, but only this liquid part, liquid gaseous part, whatever cut. The most important thing that it's conducting part, and so it can work on this process that is simply just cooling down. And in the Earth, this process is not so effective, but it's very dramatically effective in Jupiter, for example. So in this sense, and finally, you can feel what is the entropy and why it's so useful. Actually, entropy is the ratio of the heat flux on the temperature. So this is how many temperature is required to rise the heat flux, for example. So we can, if we change some part of the entropy, we can change, for example, from the heat flux. If we rise, then the entropy is rise. If it's cooling down, like in present situation, then the heat flux is diminishing, and so everything is cooling down. And anyhow, we can very precisely estimate this term and work out how this cooling is working. So, and also there is adiabatic pressure and so on. So we can also further simplify all this equation, and eventually we arrive on the system which is written like that. And in my previous lecture I explained all these terms, so I hope that you all know all of them, and also the dependence of the adiabatic temperature takes this form actually, and all these parameters are very well known. And also you see that here we again have this S derivatives of S with time, and it's working like a cooling term. And also, of course, there is some heating term, and there is some term in all this in all this stuff which is responsible for the viscosity. Oh, sorry, not viscosity, not viscosity, but diffusion, thermal diffusion. Here this term responsible for thermal diffusion, and it also has somehow sink nature, that it's just some heat is sinking in this place. And also we of course have boundary condition, and there are not only 6 boundary condition on velocity, there is also boundary condition on the entropy, which actually constitutes that the gradient of the entropy on one boundary and another boundary is actually equal the difference between subadiabatic flow which is more than adiabatic, and adiabatic flow. And also just we need one more boundary condition just to resolve the to resolve the gravitational potential. Also, there is some relation, like I show you to you. And let's go to the final stage. We just now we make some sort of the conclusion and formulate all the equation which constitute this system, final one. Before that, I was explaining in every detail how each term appears. Now I briefly proceed from all this term. And now let's draw the conclusion. Let's draw the conclusion. And this conclusion, in this conclusion, we just summarize all the equation and start from this equation. Oh, okay, from this equation, so in somewhat in reverse order. But we will keep the number of the corresponding equation as it was originally, just for you to understand. And actually, all this text will be available, so you can just see. Because there is also the processes that we return back to some equation to examine it, and so you can easily use this text to return and to understand. And pick up, of course, we start from the entropy equation. So let's write down all the equation which is working in this system. We get the substantial derivatives of the entropy. And it is equal kinematic diffusion, which is usually turbulent diffusion. And of course the diffusional term, which is actually Laplace operator acting on S. Again, the small s is not the entropy itself, but just deviation from the adiabatic state. And also there is source, adiabatic source of the heat, Q adiabatic. I already show how it works, and it's divided by, and also quite well known, adiabatic density and adiabatic temperature. All these things could be changed. I mean, adiabatic temperature and adiabatic density, and as well adiabatic heat flux. And so these things could be changed, of course, and they change only with radius, because this is spherically symmetrical case, and we already spoke about that. I just remind you. And this is somewhat new formula which appear from the consideration that the influence of the pressure on this energy stuff and on this Archimedean stuff is actually negligible. But I'm not speak here in every detail of this statement, but it will be a separate chapter which is devoted exactly the verification how good is accuracy of this approximation, and so it can freely neglect by the pressure term and so on. So it will, separate chapter will be devoted by that, and also characteristic value we will estimate from the nonlinear term. So then the next equation, which also working here, is again very simple. It's just continuity equation, which is just because we neglect by the effect which are related with the sound of with the speed of sound, so we can completely neglect by substantial derivatives for the in the law of in the continuity law, sorry, in the continuity equation, we can completely neglect by the substantial variable, taking into account or not, taking not into account sound speed and sound effect, just filtering them out because we are not interested in them. And this takes a very simple form. It will be divergency of rho adiabatic times V. And it's constitute formula 47b. And then neglecting, then as already was, again I just mentioned that here we neglect by acoustic or actually acoustic changes in the density. So eventually we have this part. And also again we can refer that pressure is working. And let's now proceed to further equation. Now we take it from the previous part, and they are very important. And so we just proceed to the equation. Of course, the most important equation, Navier-Stokes equation. And this Navier-Stokes equation can be written in this respect in such a form. dv. Here substantial derivatives is quite important, and we just estimate it. And it has two contributions of the viscosity. First contribution is just viscosity which is related on the strain tensor, and it's better represented not via Laplace but double rotor, because it's when you are using double rotor, then you have a better understanding how this actually vector value is working, not the Laplacian, because if you use the scalar Laplacian, it will be not true. Actually, it's much more better to use double rotor in this equation. So, of course, here there is V. And then also there is the contribution, which is actually related that generally speaking, the velocity field is not exactly divergence free. So there is some contribution that it's at least in the Earth, of course, it's we can regard that it's almost divergence free, because the deviation of the density is just about 10% or even less than 10%. But if you consider the Jupiter again or Saturn, then we have very big variation in the density. So we cannot neglect the following term. And this following term is written like that. Here, of course, rho adiabatic. And then we have a gradient of the divergence. And then maybe perhaps the most important term in this equation, because if we are working in the rotation system, actually non-national rotation system, we have Coriolis term, which is in dimensional units, can be written like that. Here we have unit vector in the direction of the axis of rotation, and then it's just multiplied. There is a cross vector multiplier on the velocity. So here we end up with the Coriolis term, and it's interesting to mention that this, this Coriolis term is first of all balanced. I slightly changed the order which was in the original notation just for your better understanding, but of course it's the same. So there is also first things which work to balance the Coriolis flow, and this is first thing is not related to the velocity, but it's related to the pressure. More precisely to say, it's related to modified pressure. This modified pressure not only include the ratio of the pressure, or more precisely the deviation of the pressure from the adiabatic state divided by the corresponding density, but it is also include gravitational potential, or maybe more precisely deviation of the gravitational potential of the gravity field. Okay, here we close, but we forget the main ingredient. What do you think? What is the main ingredient which is actually drive all this kitchen? What else we need? No, buoyancy force. Because actually buoyancy force, it has many names. It is buoyancy force, Archimedean, acceleration, and somebody name it. In this particular case, it's actually this buoyancy force or Archimedean acceleration is first of all, in the simplest way, of course, it's driven by the entropy. So it can be written, let's read it specially here. We just fit that quite successfully. And this entropy stuff, of course, first of all, it has entropy, or more precisely, the deviation of the entropy from a adiabatic state. It's fully dependent on the three coordinates of the space and time, of course. And then we have this combination of the expansion coefficient, adiabatic temperature, then Cp, and of course there is the gradient of the gravity, adiabatic gravity, which is just ordinary gravitational acceleration. On this boundary, it's about 10 meters per square second, about 10. So we have the driving term, and let's keep the original number of this formula, 4.4, right? Just to collect everything in one place. All the systems which are finalized this presentation. And then it's necessary to mention that there is also some addition to that. But if you can see on this equation, you have equation for the entropy, you have full equation for the velocity, you have equation for the not divergence free, but divergence of more precisely to say momentum, actually, because it's not velocity, but multiplied it by the density, it's sort of the momentum, normalized momentum, if you like. You normalize it on the in this term. So actually, all this equation is already enough. If you just add the boundary condition to this equation, let's write them down. First of all, the boundary condition, which related to the energy, actually, to the entropy. Let's write it first. So we are adding boundary condition. Let's just state it. So there is actually complete system which we can resolve. And it's important to mention that in this system, there is no need to resolve for gravitational potential, because it's very effectively collecting this effective pressure. And also we have very simple driving term. So now we can just state the boundary condition, and already on this stage we can solve the system. Of course, we are substituting proper boundary condition for our task. So let's start from the inner boundary. Inner boundary is denoted by I here. So we take the derivative of this entropy or deviation from the adiabatic entropy, and this is the deviation from R, because actually the heat flow is preferably going in the radial direction. And at the first approximation, when we consider only adiabatic component, they depend only on radius. So it's quite straightforward just to define its radial derivatives of the entropy and express it in terms how many heat we put in the system or we take from the system, whatever we do. So in this case, it working like that, minus T A, oh, sorry, not T A, here we should distinguish not only, so just for simplicity, we will not repeat here that this is adiabatic temperature. Of course, it's adiabatic, but precisely on the inequal. So we will not build two term adiabatic and E just put here just I. So it will mean that this is adiabatic temperature directly on the inequal. And in the same way, we should write here. Oh, okay, maybe not enough space. Sorry. Okay, let's just state the boundary condition. It's important to mention that it's clear that it's equation, but now we proceed to the boundary condition. Let's give the extra space, especially for this boundary condition, because it's rather important. And then I'll write down this T I, rho I, again the rho, and also there is transport coefficient, kinematic transport coefficient, which is actually thermal diffusion coefficient. And more precisely to say, not thermal, but entropy diffusion. But there is, if we go to precise denoting, but actually it has a nature from the thermal diffusion coefficient. And here we have this ds by dr. And it's important to mention that these derivatives is taken at r equal Ri. So this is actually the term which determines the heat flow due to the variation of the entropy. And on the boundary or variation of the entropy could occur only in radial direction. But finally it's depend on the input or output heat flow. So we made this output or input heat flow flux like Qi, and because this is not complete heat flux, but the normalized heat flux, and we normalized this heat flux on the area, and the area of the outer boundary is of course the spherical surface. And it's obvious that its area is equal 4p Ri in square. So if we have this flux which enter in the boundary, what means enter? What means that it supports the convection. How it can add to the convection. So in our term, it should be greater than adiabatic heat flux. So if it's this flux, normalized heat flux, of course, if it exceeds the adiabatic heat flux, then this heat flux working on the creating the convection. In opposite case, if it's less than adiabatic heat flux, it's acting against convection. It's actually stabilizes this place. And in terms of the inner boundary, we always have this flux contribute to the convection. Because this heat flux could be, first of all, of course, due to the cooling of the planet. But maybe more important contribution could be from the compositional difference when the heavy particles are descending on the inner core and lighter particle is going up. So actually it's it's always positive. But what means positive? If we consider the adiabatic heat flux, so it can be represented by this simple formula. It depends only on R, on the spherical radius, and of course we are taking these derivatives. we are taking this derivative of at the inner boundary. And you see that here we have plus, but this gradient, because we have on the upper, the more densely we are going into the liquid outward core, the more temperature is. So it has negative gradient. So this term, if we calculate it precisely, this will give negative. So it will be just the part which is removed from the total heat flux. So this is the total heat flux, and this is adiabatic heat flux with minus sign. So actually here we have a difference. Let's just clarify it. So it's just delta Q E. Maybe to write. Of course, divided one. So this is constitutes the formula for 6C. Yes, of course, in the same way, in the analogous way, we have the same similar boundary conditions, but on the outer boundary. So on the outer boundary, we write it like that. The outer rho outer K is by TR. Let's stress that this K is small K. This is capital. Let's just stress, just for you to understand that it's actually different values, but they of course related one to each other, but nevertheless originally slightly different. And then we have proceed further. R equal R O and equal. Of course, here we have output heat flux RO squared, and then again this K, capital K, and adiabatic temperature. But oh sorry, again. This is direct R0. Okay, this constitutes another delta Q O. Just for your convenience and better understanding, I added this term just for you to understand that we have not from this formula we actually have the if it's with positive sign and this heat flux is larger than adiabatic one, then we have positive contribution here, and this positive contribution corresponds to the support of the convection. But if we consider the outer core, then this is again the same rule, but from the recent experiment they found that perhaps this is smaller than 0. Just say it. Perhaps this is smaller than 0, and this one is definitely more than 0. And this, when it's smaller than 0, it stabilizes the convection, actually remove. And here it's of course in favor of the convection. Let's support convection. Another situation, for example, on Jupiter. In Jupiter, this one is the most important. So, oh, no, sorry, this one, which is output. Here it's stabilizing the Earth, but in Jupiter it's in reverse order and it's produced the largest magnetic field. Okay, so we finished with this boundary condition, which is related to the entropy, quite important. Then we should proceed to the boundary condition for velocity. Let's write them down. And this is, here we have two boundary conditions. For velocity, we have 6 boundary conditions. Because each velocity has 3 components. And we have component on the outer boundary, on the inner boundary. So it will be 6 boundary conditions. And it's interesting to mention that the order of the Navier-Stokes equation from which we taken this velocity is the equation effectively of the 6th order, because there are 3 equations, 2 orders of magnitude each. So there is a match between the necessary boundary condition and Navier-Stokes equation. And also there is a boundary condition on the entropy. It's one more equation and 2nd order. So we need to add 2 more boundary conditions. So now we have right number of the boundary condition. Let's just write down the boundary condition for the velocity or Navier-Stokes equation if you like it more. It could be written like that. This at R equal RO. This boundary at R equal RO. It can be noted like just VO. This is actually the velocity with which mantle is rotating. So we supposing that we are, if we consider Earth, then we are in the frame which rotating together with mantle. And in this frame, of course, frankly speaking, this velocity is not precisely 0, because actually there is some influence. But nevertheless, the mantle is constitute more than, I don't remember exact figure, but about 80% or even 90% of the all the mass of the core. And especially we should consider in terms of the momentum, because you see that if we consider the inner core, okay, if we consider the momentum here in the core, we have some density. So to understand how this law is working, we should consider the momentum, because the second name, and maybe more acceptable, the second name of Navier-Stokes equation is momentum equation. What does it mean? It means that the product of the velocity on the distance is important. You see that here in mantle you have a larger distance than here in the core. So the velocity, correspondent velocity, of course in inertial coordinate system in which we actually then go, it's much more than here. So if in terms of the mass the difference is that about maybe just 20% is here for this boundary condition and 80%. In terms of the momentum, it will be just, I don't know even exact figure, but less than 10%. So at least in the, with accuracy of 10%, and it's quite good accuracy, because, for example, we also use this accuracy in estimation of the density. So here we have just 0. Of course, this simplifies stuff a lot. However, there is another boundary which is correspond to the R equal R I. R equal Ri. And here we can denote it like Vi. And this is not necessary 0, but of course there are some models which regard it like 0, because the differential rotation of this inner core could exist. Of course it's small, but in some sense it's enough to produce some velocity, shear layer and other structure. So to make the right things, of course we should take into account this value, but of course it's not so big, and it's in spherical coordinate system can be written like that. This is actually cylindrical radius. Cylindrical radius, and it's also contain relatively small extra omega velocity, which is in our mantle rotating system is rather small one. And here we have a direction only in azimuthal direction. So we finish up with this. Here we have 6 boundary conditions, as I already told, 3 from here on the outer boundary, 3 on the inner boundary. And this original number of this formula is, okay, I just omit 4. It will be 6, A and B. Of course, from chapter 4, I put 4 here, otherwise it's not fit. So we completely formulated our system, and we write down all the necessary equations, but we just forget about the gravity potential. So we very effectively combine it in the effective pressure. But if one would like to some occurrence to understand how this gravity potential is working, he just can solve this equation. Then he have a reduced pressure, and this reduced pressure together with reduced gravity equation, which look quite simple. It's just Laplacian of gravity equal 4p g. Here we have rho p, known thermodynamic. It is the density under constant pressure. And then we have this p, exactly this p which appear here. And then we have density derivatives on R with constant entropy, of course multiplied it by entropy, which is somewhere here, this entropy. So this is the equation for the gravity potential, from which we can find it after we found the pressure, after we found this entropy. And so if we would like to have the gravity, then it's constitute for B here, formula. And of course it's also require boundary condition. And boundary condition in this case are quite simple. And they look like that. It's a formula for 6EF, for 6E and F. it's just, as already told, this is the most important on the boundaries is radial derivatives, and of course, so we constitute very simple boundary condition du by dr at two boundaries, at both actually boundaries, at r equal ri and at r equal r naught, they simply is 0. Okay, I formulate everything, but I forgot one thing. Maybe you know who follow my previous lecture, maybe he said that what I forgot. Which condition I forgot one. Rather, I don't know how to say important it's or not, but which condition? If you follow my previous lecture, you can answer this question. I forget one thing. No, it's global condition. If there is boundary condition, there is local condition, which we have the differential equation. But here you see that the boundary condition for the entropy, this entropy, both are in the derivatives. And usually, if you use derivatives boundary condition for second order equation, you should have an additional condition just to determine all this stuff. What this condition? I wrote about, I spoke to you about it. Can you? Just see your previous notes. Okay, I will give you a hint. 4.3b formula 4.3b. So did you found? So this is the actually integral condition. As already told, if we have the boundary condition which formulated on the derivatives, here we have boundary and derivatives of it. So in this case, for example, when we have Laplacian, at least for the very simplified case, it has constant, its solution constant, and 1 over r, Laplacian solution. If we take the derivatives, we remove constant. So we are out of one free constant. There is only one free constant. And to get another free constant, we should formulate the integral condition. Let's put it maybe here. It's not so big. There is integral in all space. Okay, I will not wrote here that it's in all space. This is integral from the relation, which actually it's related to this, so it's very close to it, and actually this is integral of entropy times rho, and in this case, of course, adiabatic, and all over the space, all over the liquid core, and it's just simply 0. So actually this condition is that the weighted entropy is declining from the, because this is the deviation from the adiabatic state. And if we integrate all this deviation from the adiabatic state, it finally should give 0. So this derivatives not only mathematical help to this boundary condition, but it also has physical meaning that the total deviation from the adiabatic state should be 0. And so this is a physical meaning of this. Mathematical meaning is, of course, to make the complete system of the of the condition which allow us to precisely to resolve this equation. So there is two meaning of this stuff. Okay. So actually we formulated everything. What is constitute derivation of this equation? Okay. Okay. And on the next we will discuss how precise is this system and estimate from the nonlinear approach the characteristic value of the system. But now there is a time for your question. Okay, sorry, I just remind once more that we can resolve system for the velocity and entropy actually separately. And then if we need some gravity potential, we can resolve it after that. So there is a good point of representation via entropy that we can resolve all the system, which is in calculation and so on, quite simple, relatively simple. It's actually it can work almost in any planet and even some stars, but it's relatively simple and it's almost like in Busse form, very close to the Busse form, and it's just slightly more complicated. And this complication is that we have, instead of the divergence at v, we have the divergence of this momentum. It's not so big deal to treat it numerically, for example. And the other difference is in the boundary condition and this global condition. Oh, I should number it. Okay. So please, your question. Okay, is there any questions? Okay, everything is clear? Is everything clear? I hope so, of course, that everything is clear. Okay. Is there any question? No? Okay, anyhow, this text of all this stuff will be available. So, huh? 451? On the screen. Yeah, okay. 451, yes? It's just collection of all equations. 4.1, it's initial equation which we have, all of them are actually 4.1. It's just in this chapter, it has 1, 2, 3, from A to E. So all this equation are the initial equation, and this is the initial equation. As I already told you, there is the continuity equation, then we reduce it, there is the gravitational equation, then we again reduce it, and there is equation of state, and we reduce it to the dependence on the pressure and entropy only. And of course there is the equation for the entropy. Here it's present in initial form, but what I finally show, it's not for entropy itself, but only for deviation from the adiabatic entropy. Everything deviation from the adiabatic, deviation from the adiabatic density, which actually drives this buoyancy force here, which originally from here. And of course, only velocity has its own meaning. All the other stuff, we reduce it to the deviation from the adiabatic state. Yeah. This one. Yeah. We express everything in pressure and entropy. We express temperature variation, we express gravity variation, we express what else? Okay, everything excluding velocity. Velocity is playing its own game, but everything excluding velocity is defined in terms of the not pressure itself, but the deviation of pressure from the adiabatic state, and also not entropy itself, but the deviation of the entropy from the adiabatic state. Because of course this deviation is very small, and all the game is around it, because the deviation is just roughly say it's 10 to minus 3%, 10 to minus 3%. So actually it's 10 to minus 5, something like that. So this deviation is very tiny, but nevertheless, namely this tiny deviation from the adiabatic state creates the convection.
So how to choose the rho A?
Rho A?
That's 4.1, first term on the right side.
This one?
Yeah.
This rho A is adiabatic density.
Adiabatic density.
Everything is the adiabatic here, excluding the variables.
Okay.
So actually this is the approximation, almost adiabatic approximation. So we are working very close to the adiabatic approximation. So we are getting this result like that. Okay, one more question please.
Approximation. What is the motivation for assuming an adiabatic approximation? Is there any validation for assuming?
It's very important meaning. It has very important meaning. If you want effectively to solve the system, you have to do that. Because if you will not use this approximation, for example, even in the case, usually people regard that it's normally not to use entropy. People somehow avoid entropy. They didn't like it. I don't know why, but they prefer to work in the ordinary pressure and temperature, for example. And I devote this, in the next chapter, I will estimate the accuracy of this almost adiabatic approximation, and also I estimate from nonlinear point of view typical values and compare with those. But after that will be special subject where I show that if you use pressure and temperature instead of pressure and entropy, you have much more complicated equation. They even, I don't know, it will be hardly possible to resolve them in numerical as well. Much more hardly than that system which I showed you. So this is a very strong motivation to have the almost adiabatic approximation. And another point is that here we just slightly change the fold, and it's taken into account all the effects, even with rather big variation of the density. So in few words, it's like that.
But for entropy, we have separate equation. Suppose what is the difference? Suppose we consider density difference of pressure and temperature, but entropy can be calculated with separate equation also.
It's maybe not right way, because at least in this problem, I don't know, maybe another problem work another, but in this problem, the major essence of all this problem is that everything is near the adiabatic state. So if you operate very near the adiabatic state, and the adiabatic state is initially defined by entropy. So adiabatic state is just the entropy is independent on the space. It depends only on time. I mean total entropy, of course. Not the variation, not everything, but the total entropy. No. So actually, this is a very good approximation, and it has very high accuracy. So actually, of course, in some applications, maybe many applications, technical applications, it's more convenient to use the temperature. But namely in this application, much more better is using the entropy variable. Because even the equation, as you show in one lecture, because even equation become very complicated, and you can maybe it's possible to resolve them, of course, but it is much more effort and not so precise. Actually, it's also important.
But the equation, second equation from Plato, entropy equation.
Yeah.
Right side is operator operating on gradient of
Yes.
temperature.
Yes, it's temperature, but it's just initial equation. The final equation, which I wrote here, we just here it is. You see, you actually rearrange this equation that instead of the temperature you have entropy.
Okay.
You just rearrange the equation in the way that it's and here, of course, not the initial playing game. Here there is adiabatic flux, and all other things are accumulated there.
Is it T or it is S? Is it T or S? Just I want to know.
Yes, here we I don't know where is here to get this equation.
Yes, it should be not T, but it is S.
Yeah, we expand in a few words. We expand T in terms of the pressure and in terms of entropy.
Oh.
And then eventually contribution from pressure is very small.
Oh. Okay.
So we neglect by contribution of pressure and left only with entropy.
Okay. But T equation is not here.
This is sort of the game.
Okay. The T equation is not here. What is the T equation? T in terms of pressure and the entropy.
T equation. I'll write down. Okay. I will write down equation for T. Okay, well, let's put it here. It's just thermodynamic equation for
I understood.
equation for T, and it's can be written like it's our previous formula.
Yeah, I have seen this.
This equation for T, or more specifically, is the deviation of T from adiabatic state. So T over T, it's small variable, and it's expand in two terms. One is partial derivatives from T under the constant pressure, multiplied it by pressure. Of course, deviation from the adiabatic state. And the next
minus
next term, T plus
plus TS
plus
and TS.
TS times S. And this is actually formula 4.2.
Adiabatic.
4.2 G. And the play is that this term is so small in comparison with this term that we just simply can cancel out it.
Okay.
And then we arrive to this.
Okay. So in same equation, rho into T. Is it rho into T? It is non-linear contribution, right?
Yeah, this rho into T is also important because the same game, again we neglect that and keep that. And eventually this deviation of rho is coming to the Archimedean force.
Okay.
This Archimedean force or buoyancy force. And it depends again only on entropy.
Okay.
Actually, the main play here is that the pressure against entropy contribution is negligible.
Negligible. Okay.
So the main plane is around this stuff.
Okay.
So it's not wise to keep pressure because it's small. More precisely, of course, not pressure, but deviation of the pressure from the adiabatic state.
Yes. Okay. Nice.
Okay, thank you. Okay, it seems we finished. Okay, it's not my invention. Vladimir also used this approach very much. But yeah, I got the impression, but that people just afraid. Because the things I presented here is just about the temperature contribution. But there is compositional contribution, which constitutes the second derivative. And the much more complicated boundary condition. Because in boundary condition, when you have addition, not only temperature, but the diffusion of the light consistent, so its equation becomes much more complicated. But nevertheless, it's possible to push this approach, and in Braginsky, okay, even Braginsky and Roberts wrote the paper which still named 100-page paper. They wrote about 100-page paper in GAFT. Yeah, it was special issue. Here they considered all the stuff. Yeah, please.
So in the mantle convection, can we take the Coriolis force effect will be there, or?
Yes, the Coriolis force will play a very important role, of course. It's one of the central forces. Actually, especially when we consider convection, after my next lectures, of course, I will be only about convection speaking about. And if we consider convection, there is, from my point of view, maybe one of the main breakthroughs of the humanity.
Oh.
Because this convection system, which I wrote here, was resolved almost precisely. You see that this is 8th order system, because the 6th order in Navier-Stokes equation, 2nd order is equation for the entropy, and so it's 8th order system in partial derivative. And it's possible due to the smallness, relative smallness, if we take the ratio of this, maybe better to put here, if we take the ratio of for example, of viscosity term to the Coriolis term, we exactly get the Ekman number. It's 10 to minus 15. So and it's effectively enter like the small parameter near high order derivative. From one point of view, it's a very difficult things to calculate. But from an analytical point of view, you have just first using that stuff, you work on the boundaries, and on the boundaries there is a thin layer which has a thickness of the square root from Ekman number, and here problem becomes two-dimensional actually, because we can work only in the boundary layer, and you can almost precisely to manage with this Ekman boundary layer. Then there is another, not boundary, but shear layer like that, Taylor column, maybe you hear, where the major convection occurs. And in this, again, we can expand in Ekman number. And finally, the final thing is that we reduce this 8th order partial derivative system just to one ordinary differential equation, one second order, just one second order differential equation. Of course, with plenty of parameters, because every parameter needs the picture which we involve from this stage. But I think that maybe it's one of the main achievements of the humanity, of the mind, or whatever you like. It was started by Busse, Then it was, of course, I will speak in my next lecture, but it's. I also made some contribution to that. Okay, so but nevertheless, from my point of view, it's quite impressive that so complicated system we reduce it just to second order ordinary differential equation with, of course, putting on this boundary condition, and so actually it depends only on z coordinate eventually. The final system, which of course the characteristic system, not the, which involve plenty of parameters. Of course, it's also linear solution, but nevertheless, it's quite impressive, and it's possible to compare it with the full numerical approach, and accuracy of this asymptotic solution is very good.
The fluid is only thermally conducting, not in the mantle. The fluid is only thermally conducting, right?
In the mantle, there is some model that assumes some convection in the mantle.
Mantle convection, right?
Yeah, there is model of the mantle convection, but it's very slow convection. Much more slower than in the Earth core. In the Earth core, of course, convection is also not so fast. It's just a few millimeters per second, even less than few millimeters per second. But in the mantle, it's even slower. So the typical time of the convection in the Earth is about 1,000 years. So we just can directly see how magnetic pole is rotating about the axis. The typical period is about 1,000 years. More precisely, 5,000, something like that. But in the mantle, typical time, million years.
Okay.
So it's quite slow. And it's maybe not precisely convection because there is some intermediate state between the rigid, at least on our time scale, we can treat the mantle like the rigid body. But of course, on the larger scale, it will be treated like a liquid.
So it means the convection is slow because of the rotation, right?
No, it's not. It's not dependent on that. Independent. Rotational rate also have some stabilizing effect, but this stabilizing effect is the Taylor condition that in the direction of the axis of rotation, we have only small changes, but we can have dramatical changes in the cylindrical direction and in radial direction. So this is perhaps the main point.
So we are getting volcano liquid from the mantle or from
sorry,
volcano's liquid lava.
I don't.
Lava, magma, lava. That comes from the mantle or somewhere else?
Yes, of course, the lava flow and other flow. Of course, they on the. I don't remember exact numbers, but somewhere. If you go down by about 100 kilometers, or maybe some tens kilometers, so you will have this higher temperature. It's a quite known experimental fact. If you are going down, then you reach the temperature is rising, and there is some boundary where the temperature is rising so much that it becomes sort of the liquid. Not precisely liquid, but sort of the liquid. And because this process is somehow chaotic, so we have at some places very thin layer or very of the rigid substances, and in some place we have sort of the breakthrough, and here there is this event appear. Perhaps it's even inner core could be responsible for that, because from the inner core we have some sort of the, not precisely fluid core maybe, more precise to say the fluid core. There is some, there are many theories, but about this convection and mantle, about how it's connected with the lava flow, with volcanic eruptions. But frankly speaking, there is no family state theory. most of them are just suppose some chaotic behavior and so on.
So what is contribution of rotation of mantle to the Earth?
You mean that rotation of the mantle?
What is the contribution? For example, Earth's outer core, due to the rotation of that core liquid, we are getting the magnetic gravitational field, for example. So similarly, what is contribution of rotation in the mantle to the Earth?
Mantle is rotating at least on the time scale, which is below some maybe 10 or maybe even hundreds of thousand years. On the time below this value, we just can suppose that the mantle is in the rigid body rotation.
Mm-hmm.
And of course, on the more longer age, up to million, billion, whatever you like, maybe some thousand, maybe hundred thousand. I don't know. Nobody knows exactly. But on the larger scale, it can work like the liquid. But in any scale, there is no way to produce magnetic field.
Okay.
In any case, just because the very low conductivity. But in the liquid core, the conductivity is rather higher. Just because it's just a thermal. It has very high conductivity. So this is the best way to produce magnetic field. And by the way, the energy of magnetic field is million times greater than the energy of the convection itself.
Okay.
So this is a very effective producer of the magnetic field. It's even has this tiny value of the convection, and it's produced huge magnetic field. In this term, the magnetic field of the Earth is much larger than the Sun. While if we consider new numbers, on the Sun we directly measure kilogauss. On the Earth we measure about Gauss field. It seems that 1,000 times less. But if we consider the energy, then the energy of the suns, which is we also directly see the velocity of the sun. We see how we even can understand how it's working inside the sun, because there is an analog of the earthquake. There is a sunsquake, and they are of course much more intensive than earthquake. And just using this sunsquake, just to figure out what is this inside the sun, we can find the velocity, we can find density, we can find everything. Even more precisely than in the Earth, because only by the reason this sunsquake is much more intense. And so eventually we can easily estimate it, how much is the energy in the kinetic, in the velocity, in the relative velocity, of course. And it means after that we can draw the conclusion that this kinematic energy is even greater than magnetic in the sun. But in the Earth, the reverse situation. Not simply magnetic energy greater than kinetic, but million times greater.
That is the reason. It means the Earth outer core rotation will not affect the mantle rotation, right? Earth's outer core rotation and mantle rotation, do they have any correlation? Otherwise, they are independent.
Yes, of course, there is also correlation, because actually this problem is very much linked to the length of the day. Because actually, of course, we suppose that the angular rotational rate in this formula that is constant. Of course, it's the simplest and in some way, but it's not constant, of course. It's not constant, and it's changing time and changing the direction. Direction, you have this variation of the angular rotational rate of the. There is the I forget the English name. Due to the influence of the moon, for example. This is tide effect, which play rather sufficient role in the changing of the angular rotational rate from the moon. And by the way, there is almost the same tide effect which we have from the sun and from the moon. Moon is much smaller than sun. but it's much more close. So eventually moon and sun has comparable effect on the rotation of the Earth.
Oh.
And of course on the ocean, on the sea, that we have this changing of the in the tides and so on.
Means we had to study both models separately. Earth's outer core model separate and mantle convection separate. Can we combine both the models?
No, you are not right. They are not separate. They are quite tightly linked. The reason why the magnetic field energy is much more greater than kinetic is not working direct. It's working in the way that maybe you know that if we have the velocity in some direction, then if you have the magnetic field, so the interaction is V cross B. V velocity, B is velocity vector, B is magnetic vector, and V cross B. So the main effect is when they are perpendicular. And when they are almost in the same direction, the effect is actually cancelled out. So this thing is working like that. Not the velocity diminish, but the velocity could even very small. But the magnetic force, magnetic field has a tendency that it tends to be along with the velocity. And the more they are following the velocity, more they parallel to the velocity, more value it can reach. So eventually, if there is such a tendency, it can reach tremendously big value, but staying almost parallel to the flow. And it's eventually, so this working in some tricky way, not direct.
Not directly. Thank you.
But the dependence is very strict.
Yeah, okay.
Because maybe one of the first work of the Braginsky was almost axisymmetric dynamo or something like that. So if we have some symmetry and it's strongly related to the flow, then we could create very strong magnetic field. And vice versa, it's like on the sun, we have the magnetic field which is not so strongly parallel to the kinematic velocity. Then we have this magnetic field in terms of the energy, of course. In terms of the energy, in terms of the absolute value, of course, it could be big. But in terms of the energy, it's small. Maybe not small, but of order of magnitude.
Okay. Okay. Thank you, sir.
Okay. Thank you very much for question. My pleasure. But maybe we'll have the break because we spent 2.5 hours. Oh no, 1 hour and a half